Okay, guys, I think we'll get going. First of all, you guys are all good. You must have been good students at school because you're here. I think this is the last session of the day, and you're all here. So, very good. I appreciate you being here. Okay, my name is Mike Gurr. I'm the general manager for manufacturing and automotive here at Cloudera. Today, I just want to talk to you a little bit about open source data management for Industry 4.0. Before I start, how many of you in your companies have implemented Industry 4.0 initiatives? Just curious. Good. How many are planning to? Okay. Yep. Yeah, and, you know, my proposition is, and we'll as we get into this, you know, these are still early days for these initiatives, but there's a lot of great things happening in this area. So, look forward to talking to you about it. All right, so let's get going. And then the sooner I get going, the sooner we can all enjoy the end of the day and get on to hopefully relaxing a little bit. Okay, so a few things. I just want to talk to you just a little bit about Industry 4.0 for a little bit of background for those of you who don't know it. I'm going to talk to you about an architecture for success. You know, we've kind of put together an architecture that is working pretty well with our customers. I want to go over some key use cases. I'm going to focus mostly on the business use cases and give some customer examples of customers that have achieved some success, and then we'll talk about why I think open source is important for these initiatives. Okay, so how many of you have seen this slide before, or a variation of it? Probably a lot of you, right? So just real quickly, let's just define a few terms before we get going. So what is Industry 4.0? You know, this is a little bit of a history lesson, if you will. You know, Industry 1.0 was about steam power and just general mechanization, you know, just self-powered types of machines. Industry 2.0 was really the mass production line, right? So think Henry Ford in those days, right? Electricity was coming in, so you had electric assembly lines and things like that. The first time computers came onto the scene, they called that Industry 3.0, right? And what's really interesting now is that we're talking about Industry 4.0. It's all about cyber-physical systems. And I love this slide because, to me, the cyber-physical systems, I think it creates more questions than it does answers. So, whoa, Industry 4.0 is about cyber-physical systems. Well, what's a cyber-physical system? A cyber-physical system is a mechanism that is controlled or monitored by a computer-controlled algorithm, and it's tightly integrated with the internet and its users, and this is where it gets interesting. In these systems, physical and software components are deeply intertwined. And I'm going to propose to you, the software systems are very data-centric. And now we're going to talk about why data is so important to this Industry 4.0 types of initiatives. But before we get into data and technology and all those types of things, why are customers and companies looking at Industry 4.0? It's not because of technology. It's because if you look at it, despite years of trying to improve quality in manufacturing companies, cost of quality still amounts to roughly, on average across manufacturers, 20% of sales. So the cost of bad quality, whether it be returns or warranty claims or scrap or defects, right? 20% of sales. So anything you can do to use these new technologies to impact that's what's important, right? The other thing that's important is, you know, plant downtime, right? If a plant goes down because a piece of equipment goes down, right, that costs manufacturers roughly $50 billion a year, according to Deloitte. When you look at the automotive industry, it's even more interesting, right? You know, when you look at recall costs in the industry, first of all, 53 million cars were recalled in the United States last year, in 2016. That was higher number than the number of cars that were sold. So each car was recalled at least once on average. The other thing is it costs companies tremendous amounts of money, right? If I've got to recall a whole model year of a car, for example, it's a heck of a lot of money. $22 billion a year is what it costs automotive OEMs in recall costs. And we'll talk about, this is one of the key use cases we'll talk about a little bit later on. That's why I'm just setting this up. But again, Industry 4.0 is not because people want to implement technology, it's because they want to reduce warranty costs. They want to improve the uptime of their equipment. And in automotive, if an automotive line goes down, if the assembly line goes down, it costs $22,000 a minute. So these are the reasons we're talking about Industry 4.0, because I'm going to propose to you data and technology now, and big data analytics can really move the needle on that. And this is what we're going to be spending most of our time talking about today. So despite all of these things and the promise that I just said that, data, and we'll talk about how data can improve both quality and uptime, and Industry 4.0 is important. Guess what? We're at the beginning of a journey, right? Only 16% of manufacturers have actually even started to go down this journey, which is why I asked you guys earlier, and only some of you raised your hands, right? Most companies, and we'll talk about this a little bit later, are just on the beginning of the journey, and that's okay. But this is these are use cases that are being adopted. We're still early on, though. So why now? Why suddenly are people having this interest in Industry 4.0? There's a few really important factors. First of all, data volume, right? Why is data volume new? First of all, the price of sensors, the cost of sensors, have come down 2/3 over the last decade. So you're starting to see sensors proliferating and being, when you buy new equipment, it's typically very sensor, it's very sensor rich. The other thing is these sensors are connecting through internet types of technology, so it's very easy to connect them. So because of all those reasons, the data from machines, from smart factories, right, it's projected to grow twice as fast as any other data source, and that's including social media. So we are awash with data, and people are now saying, wow, how can we use it to meet those objectives that we talked about earlier about improving quality and improving plant uptime and throughput. The other thing that's new is, we've always had this divide between operational technology and information technology. The OT side were the sensors and those networks, and the IT sides were the ERP systems and more of the operational types. And that's been around for a while, but what's new now, too, is there's also new data sources, new types of data sources that are coming along. Things like image, computer vision. There's just a session on computer vision in retail. Well, computer vision analytics in manufacturing is becoming extremely pervasive as well. So if I'm doing an inspection process, take pictures of the product that's being produced going down the assembly line and use computer vision analytics to say, is there a defect or not? So learn what's what it should look like and detect anomalies, right? So use that in the quality control. So all kinds of new types of data, for example. The other thing is that there's a big shift now with all of this data and all this data being ingested, there's a big shift now to streaming analytics. So what I'd really like to be able to do is predict in real time, if I'm taking in these data streams, in real time that I've got a problem and take actions. Well, streaming analytics is projected to grow 35% per year into the next decade. So a lot of growth in this area. And this is causing people, when you look at the analytics space, they used to look at monitoring a specific sensor for a specific process. The whole, and people have been doing that for years. Is my process adhering to a control chart? Now, what's happening now is people saying, let me look at my entire end-to-end manufacturing process, figure out what are the factors that will contribute to my product quality or my yield or my machine uptime, and we actually can look at all of that data and do end-to-end process improvements. And we'll talk about all these use cases in a second. All right, so the data management challenge. What's been difficult in the past? What companies are struggling with, they have a very difficult time accessing the real-time data, right? So the sensor data, this is the OT kind of data, the sensor data, the PLC data from a store, has typically been very hard to get to. A, hard to get to. B, so it stayed in their silos where only a limited number of people could use it. It wasn't being used in the enterprise. That's one thing. So difficult getting to, by the way, 99% of the data in the world right now is unstructured, and only 1% of it's being used for analytics. So this data, it's being collected, but it's not really being used for analytics. So that's one thing. The other thing is very hard to get to these different operational systems as well, right? So ERP systems, MES systems. If you speak to most manufacturers, they don't have one ERP system. They've got multiple. They've got multiple MES systems. So you've got data silos on that side as well. As a result of not being able to get to all of this data in an integrated way, it makes it very hard to answer very basic questions for a machine, for a manufacturing operator. Which process variables, for example, will predict equipment failure? You can't get to the data sets to be able to get to that information, so very difficult. Which process variables affect my quality and yield? We'll show you how we can actually bring all these data sets together so that we can start answering these very basic questions. So let's walk through what we call, and this is the architecture for success I was talking about. We call this the connected manufacturing data lifecycle. And it's important, which I'll explain to you in a second. The key point here is that first steps is that we need to be able to bring together those data sets we talked about, right? So that real-time data sources that you see at the top and those enterprise transactions, from your ERP system, relational database types of systems, transactional, bring all of that data, be able to ingest all that information into an enterprise data lake where you can store it, you could process it for analytics, and then you could do very simple things like, wow, I can do BI across all, so I could do queries across all that data sources. So remember I said that example? If I've got a defect in the field, a quality issue in the field, I can search back and say, what were the sensor values for the manufacturing conditions of the day that caused that defect, right? You can start to connect those dots. That's one thing. That's just querying across the different information. We're not talking about machine learning or anything like that, but for that, we can actually, now that we're storing all of this long histories of data, we could actually go and look at the patterns in that information. So we could say, okay, looking back historically, when I had bad outcomes, either a piece of equipment failed, what were the sensor values, what were the factors that caused that? When I had my production levels went down, right? My throughput went down. What were the factors that precipitated that? And then once you understand and you build out those models, saying, hey, here are the key factors that drive outcomes. What you want to be able to do is you want to be able to deploy those models back into the stream, which is the edge, right? And monitor and take real-time actions. Right, so it's kind of interesting. We call this the connected manufacturing data lifecycle. Ooh, sorry about that. A little bit too connected. We'll let that go. I didn't even know I had a cellular connection here, so we're. All right. All right, so connected was okay. So this cycle is really important, right? And it has two components, right? Store the data, long histories of data for your learning, develop models, and then do real-time streaming analytics, right? Real important stuff. The other thing that's important about an architecture like that is we are kind of agnostic in terms of whether you do these things on-premise or on the cloud. So for example, your data lake can be on-premise, or it can be on the cloud. You might, for example, also have an on-premise data lake and spin up your machine learning jobs onto the cloud, right? So modern technologies allow you to be very flexible in the way you do this as well. Okay, but the connected manufacturing data lifecycle, right? So where do we fit in? So, and this is the old Hortonworks slide. We're going to rebrand these logos to Cloudera. I don't have them yet, but we've got great capabilities to be able to ingest that data, and we call that data in motion. Store that data, that's traditional, like a data lake, Hadoop types of technologies, right? We've got capabilities to do the machine learning workloads, things like Spark, right? And then we have the ability to be able to plug those learnings back into that data in motion. There's hooks within that where you could actually place those models so that you could do real-time streaming analytics, take real-time streaming actions, right? And we package up open source components, right? So all these open source components, we actually package up into those packages that we talked about here. And so what's our business model and why is this important? If you look at this, We're achieving all of this with open source data components, open source software components. What's the problem with that? The problem with that is that each one of these components could conceivably be at different revisions, right, and different versions. So what do? You know, what does Hortonworks or now Cloudera do? We take all those open source components, we bring them together, we freeze them at a given rev level, right, and we package it up into, in this regard, Hortonworks data flow or Hortonworks data platform at a given rev level that it corresponds to tested versions of those underlying components. By the way, when there's gaps in it in terms of being able to provide capabilities for governance and security, we provide capabilities to make it enterprise ready. Still open source, we put it back into the product, and we certify that version. Still open source, but our business model is then we provide support on it. Because when you go into production, in particular, you're not going to want to be running enterprise software that's not supported. And we also provide professional services. Okay, but the key point here is that you're using open source components that are evolving very quickly, very high levels of innovation in a controlled enterprise-ready platform. Okay, that's kind of the business model we're on. So again, open source solution that enables this whole connected manufacturing analytics lifecycle. All right, so what are the key use cases that we're seeing with within manufacturers? Now, the key thing is here, you're going to see many of these use cases aren't even particularly advanced. You know, you don't have to jump in and do machine learning for yield optimization or equipment. There's plenty of things that you can do prior to getting to that point, and we'll talk about it. So the use cases that I'm going to present to you in order going from simpler to more complex is, first of all, we can provide just process monitoring dashboards. So this is just providing visibility, bringing, you know, how are these sensors, what are my manufacturing level, you know, my production levels, what's my scrap level, all just bringing that into a dashboard so that you can visualize it. It's not even putting things into a data lake at this point, but it's just, hey, let me know how we're doing. I'll give you more examples of some customers who are doing some pretty cool, actually some cool things even in this area, right? Process 360, this is when you're starting to say, you know what, if I'm really going to get to the point where I can optimize my processes, I need to bring together different data sets. So I'm bringing together sensor data from not just one sensor, maybe multiple sensors, in addition to all of that contextual information. My warranty claims, my machine repair orders, right? So then I can start to say, whoa, I've got these events called warranty events. I could correlate them to sensor. You know, you could start bringing all the data together into one place so that you could start to do some interesting things. One example of what you could do is the notion of what we call quality event forensic analysis. And I'll get to this in much more detail, but this is the forensic analysis part of it means the event, I've got a problem in the field, a recall or a defect. I want to be able to do forensic analysis, meaning trace back to the manufacturing conditions of the day. Was it a supplier part? Was my weld speed too low? You got the idea, right? Let's be able to trace back to what the root cause of the problem was. Then you start getting to, as we move down complexity, now you're starting to talk about machine learning use cases. You start to say, whoa, okay, let's look back over long histories and correlate outcomes, meaning in this case, the need for the equipment failing. What were the factors that precipitated it, right? What were the factors that, and a lot of times these are multivariate. It's not just one factor, it's combinations of factors. We'll talk more about that in a second. And the same thing, quality and yield optimization. So of all of the, so if I'm making a vaccine, and that involved 50, it could be 5,000 different inputs, which of those optimize my yield? What combinations of them, right? And you've got to look back on long histories of what were my sensor values and what were my outputs, and you can actually determine. We'll talk a lot more in detail about these different use cases. But these are the reasons that people are starting to do, why Industry 4.0 is possible. New data to support use cases like this. So let's give you some great example here. So just the simplest use case, right? Process monitoring, operational dashboards. The point here is that, management has limited visibility to what's actually going on in their operations, right? So what do they want to be able to do? They want to be able to provide a dashboard that you could actually get that type of visibility. A great example of this is a automotive OEM. Give you a little hint, it's a European OEM. But the point is that they had 30 plants around the world. Remember I said to you earlier about how much it costs if that plant goes down, right? It's $22,000 a minute if a line shuts down, right? So lines can't shut down, right? So what did this automaker want? They wanted simply to say, from my plants, what were the production lines? What are the inbound shipments, are they on time? So we're not talking machine learning. We're not talking about pulling in sensor values. It's a very basic ability, but being able to ingest all that different information from those different sources and provide it on a dashboard, right? And get early visibility to impending problems so that you can take some actions, right? Just very simple stuff, but very important to this customer, right? And this was as I said, a major automotive OEM. Next use case, remember that quality event forensic analysis. Again, $22 billion in recall costs, right? Think about something. If for the automaker, if they couldn't determine if they've got problems and they couldn't get down to the root cause and figure out what other vehicles, for example, were manufactured under those conditions, they would have to recall an entire model year. The wrong way to do it, very heavy-handed. Wouldn't you rather recall just a very surgical number of vehicles that you knew were manufactured under those defective conditions? This is what forensic analysis allows you to do. I'll walk through this real quickly. So this is the best example. When we look at vehicle life cycle quality analysis, this forensic analysis. I call this the mother of big data use cases, and why? Because to do this right, look at all the types of big data that you have to use. So ideally, if I'm an automaker and there's going to be a problem with the car in the field, ideally what I want to be able to do is detect it early. The less vehicles that are in the market with a defect, the less vehicles I have to recall, right? So the first thing I want to be able to do is what we call early detection analytics. And you have to look at the voice of the customer, which you see on the left, and you have to be able to scrape. These are text analytics use cases. I want to be able to go to social media and say, oh, what are people's, okay, people are saying for 2010 Toyota Corolla, brake noise. And I want to be able to pull in that information and surface it. I want to be able to go through my call center, what people calling the call centers. People enter fields of information, but more often than not, they're entering it into call center notes. It's, again, unstructured information. I want to be able to pull in that text and surface it. And then that will give me early visibility that I got a problem. On the other side of the equation is I want to be able to listen to the voice of the vehicle. And what that is looking for connected vehicle streams right now, right? So we can look at diagnostic trouble codes or sensor values and start to understand which of those will give me early visibility that I've got a problem. So the first part of the equation is for automakers to say, hey, I've got a problem early. Okay, let's detect, I've got 5 cars that I've got a problem with. Early detection from that bubbled up from this analytics. But the next thing they want to do, and this is why this becomes an Industry 4.0 problem. Once I determine those 5 cars have got a problem, wouldn't it be great if I can then say for those 5 cars, what was unique about them? Was it a combination of sensor values, or was it the fact that the wheel was torqued down to the low end of the torque tolerance? Was it because it was a certain person on the machine line, on the assembly line? It only happened in his shift. Was it because it was certain supplier lot numbers, right, or serial numbers of parts coming in? The key point is I got 5 cars that I've got a problem with. I'd like to figure out what was unique about them, and then figure out what other cars, do a search, what other cars were manufactured under those same conditions, and recall only those. Right, so if I've got 5 cars, maybe I have another 250, we recall 300 cars rather than recalling an entire model line. Prior to big data and Industry 4.0, people weren't collecting the manufacturing data at sufficient detail to be able to do that in analytics. So this is why customers in the automotive industry are really trying to connect these dots. And I'll give you an example of 2 customers that were doing exactly this. So customer number 1 is, and this was Nissan. This is actually a public one. I could have put the link on there. But what they tried, they started off by saying, first of all, let's pull all the warranty data in, all my warranty claims, and then I could start to do analytics and say, you know, what dealers am I having most warranty claims from? Okay, what parts of the country are there? Are they specific dealers? Are they doing it fraudulently? What supplier parts what parts are associated with the warranty? Just very basic analytics of the warranty claims. The next thing they did was they connected in the dealership information, all the repair order data, pulling all that into the data lake. Then what they said is, let's pull in the connected vehicle data. So that architecture I was telling you about, the voice of the customer, the voice of the vehicle, and now they're starting to pull in the manufacturing data. And by the way, part of the challenge there was not just the technology of getting the data in from manufacturing, right? I'm sure many of you are working in organizations where you've got these organizational silos and getting manufacturing to share that. We had to deal with all of that, right? But the point here is this is a customer who started off very simply just putting warranty claims in and doing analytics around it and not just building out those layers. Because what you want to be able to do in this use case, this forensic analysis use case, is connect all those dots. Anyway, so lots of big data. It's a pretty cool use case. And this is just this is the discussion. Oh, so this was Nissan when they started with the warranty claim analytics in here, and then they built out the data lake for vehicle 360, and you can see it pulled together all those data sources I was talking about. So they literally can connect those dots from problems in the field down to root causes and do containment and do containment analytics. Okay, so quality and yield optimization. The problem on this one is that the quality of my product or the yield, everybody understands when I say yield, it's like for process manufacturers like pharmaceutical companies, right? Yield would be the amount of output, say a vaccine, the output of the vaccine I get for a given set of inputs or my ingredients, right? And for process manufacture, yield is a very important construct that oftentimes drives profitability. But the point here is, look, if I've got yield and I've got a very complex manufacturing process, there could be thousands of factors that drive good versus bad yield outcomes. The question is figuring out which ones they are. And trying to do that manually in your mind is impossible, because you could consider, okay, I could look at a bunch of batches and see what my output was, and I could say, well, oh, did this factor cause it? But the point is, it's combinations of factors, and you wouldn't get very far. So let me give you a great example, and this is, well, I'll get to that in a second. The other thing when you're dealing with this type of problem is, remember I said earlier, people were always looking at single processes, and we're going to move to end-to-end. Think about this use case. If I've got a manufacturing process that takes 4 steps, the problem in the old world is I was collecting data from a sensor on that one process step, but conditions in step number 1 could actually cause a failure in step number 4. Well, if I was only doing analytics on the one step, I would never get to that. So what was happening is we were getting analytical silos for each process step. So the machine learning that you can do for prediction was only based on that one step. The better way is to bring together a data lake, have all of these process steps, and then when you're saying which of these steps, what I'm saying, good or bad yield outcomes, I can consider combinations of any of these, not just one step, but every step. And we could say combinations of steps. So we could actually do a much better job on the analytics. Here's a great example of a pharmaceutical company we're working with. As I mentioned to you earlier, pharmaceutical companies' yield is a huge predictor, is a huge determiner of profitability. And in manufacturing vaccines, yield, the manufacturing process consists of literally thousands of factors. It could be the strength of the ingredients, it could be the temperature, the humidity. So figuring out which of those factors, there's many different manufacturing factors that correlated to yield outcome was really difficult. Because they were trying to do it on spreadsheets, and they were trying to say, looking at, they did literally thousands of batches, but they look at one or two batches at a time and try to figure out which of those factors correlated to a yield outcome. The human mind can only look at 2 or 3 factors at a time in combination together. You just can't do it. So this is where enter machine learning, and let the machine do the work. So what did this company do? In the first month, they loaded all the data from every sensor, from all the factor data, whether it would be from sensors or whether it be from their production, put it all into Hadoop, into a data lake. For every factor that thousands of factors for every batch they ever made. And then they said, let the machine churn through and say, let's consider one factor, then 2 factors in combination, then every factor in different combination. The machine, to do that, actually took 15 billion calculations and 5.5 million batch-to-batch comparisons. That's how many, so you could see the futility of having to do this manually, right? So they did that, and after 5.5 million batch-to-batch comparisons, they identified the specific factors that actually drove good yield outcomes. And they called that, once we said, hey, here are the things that are the most important to monitor, and they called that the golden batch, because here are the 5 things that we really need to monitor very tightly if we want to get good manufacturing yields. And this next slide just kind of shows you, and I won't get into a lot of detail, but it just kind of shows you the types of analytics you can bring to bear. Because if you look on that chart there on the lower right corner, those are each of the main factors, and it showed you which ones correlated to yield outcomes, right? So in a very visual way, you could identify, okay, of these gazillions of factors that I have, these are the ones that are the most important, these are the ones that correlate to yield outcomes, and these are the ones I need to measure forward going on. So this is an example of yield optimization and why you need machine learning to be able to do that, because simply the sheer amount of data that you need to do to develop out these insights wouldn't be, or just aren't possible to do manually. This is another, Micron. This is a semiconductor chip manufacturer, and a chip manufacturer is made up of wafers, right? And when you manufacture a chip, it actually takes 6 weeks to manufacture. It goes through one wafer operation where they do photochemical etching. Then it goes to 6 weeks to. So the key thing that they wanted to do is, if there was a defect, they wanted to be able to detect it immediately and stop working on it, because otherwise you could have as much as 6 weeks of wasted effort in the manufacturing process. So what they did in this use case is they took, if you look, kind of interesting, 1 trillion measurements per day this company's doing, electrical testing, plus the key thing here is they're taking pictures of that wafer, and what they've done is they've developed out algorithms that say, hey, this is what good pictures look like, this is what it should look like, and then when there's a defective process, they can detect the anomaly. So it's anomaly detection. And what it did was, it used to take them 7 days to determine whether a wafer was bad. They've brought that down to in under an hour now in terms of using big data analytics and anomaly detection to be able to do that. Another great use case, and there are public reference on this as well, so they speak about this use case a lot. Okay, just last one, equipment predictive maintenance. As I mentioned to you earlier, predictive maintenance, plant downtime costs customers $50 billion, manufacturers $50 billion a year. Just a little bit of background on maintenance strategies for companies, just because there's 3 types of maintenance you could do. Corrective maintenance, and this is what happens when our tire blows out. We do the maintenance operation, meaning fixing the spare tire, putting on a spare tire only after it fails. Very expensive, right? Because the car has gone down in the meantime, or the piece of manufacturing equipment has gone down in the meantime, and it also has a negative impact on quality. Why? Because before that piece of equipment failed, it was likely not performing well, and therefore contributing to bad quality. The next type of maintenance is called preventative maintenance or time-based maintenance. And what we're saying in this case is like, I change my oil every 6,000 miles or 12,000 kilometers. And what's the problem with that? The problem with that is oftentimes you are replacing parts that are still good, right? If I do just on a time basis. The most advanced case, and this is where we're working with customers, is what we're calling predictive or condition-based maintenance. Because if I could look back over time and identify that these were the parameters, or these were the factors that if we measured them, predicted when this piece of equipment was going to fail, and only take actions then, you're actually doing maintenance based on the condition of the product, rather than simply by replacing it on a time basis. So it's much more efficient. What you do is you use as much of that, the life of that asset. You minimize the service you have to do while still keeping uptime good. One company that we're doing a lot of work on this was Navistar, and what they did was they connected all of their engines up. If you look at it, 475,000 vehicles were connected in the field, and they built out models to determine when those vehicles would need maintenance. And what they actually did is they reduced the cost of maintenance by 40%, as compared to time-based maintenance. Even a better example of this, which I'd love, this is an old example, but it really speaks really well. This is the Metro Transit. This is the St. Louis bus company, basically. They're the public agency that runs the buses. And what they were saying, they had a lot of old buses that they had to eventually replace because it was so expensive to maintain them, using time-based maintenance. And what they said is, let's get away from that. So what they did is they outfitted their trucks, the buses. They actually not connected, they put instrumentation in the buses, and they said things like, okay, let's collect how many times the bus driver hits the brake. What's the brake pressure? How much time was the spending in traffic versus not? And they used all of those variables to predict when brakes, for example, needed replacing. So rather than replacing brakes every 10,000 miles, they figured out, based on how many times the bus driver hit the brake, how hard he hit the brake, what speeds this guy would drive. Well, what they found is, as you can see here, they doubled the life of many critical parts, right? And that increased the economical use, by shifting from a time-based maintenance schedule to a condition-based maintenance schedule. They doubled the life of critical parts, and they increased the economically useful life of those buses by 30%. So they would have normally had to throw those buses away because they were too expensive to maintain. Rather than that, they actually increased the economically useful life of those buses by an additional 30%, just because they didn't have to maintain them as often and in such an expensive way. Okay, so just one or two more slides. We're going down the stretch here. So the road to big data transformation. So as I said, our companies have different levels of maturity, the companies that are implementing. at the kind of the basic level of awareness, they're focusing on an individual process. That may be building out an operational dashboard. No machine learning. They haven't even built out a data lake in these types of cases, right? And by the way, people have been doing this for a long time. There's nothing particularly big data about this, right? But now they're starting to say, whoa, you know what? To really optimize my processes end to end, I got to collect lots of different sensor data so I can kind of do a better job at machine learning. I've got to bring together both real-time data and the transactional data. So we got to start building out data lakes. So you bring all the data together for analytics. This is the phase between this phase 1 and phase 2 where I would say the vast majority of manufacturers are. They're just starting to really think about how we can bring these data sets together, right? Okay, so then you've got customers who are actually built out the data lakes, and now they're starting to think about, okay, what do we do with it, right? We're going to start to do some optimization use cases. We're going to start to use this long histories of data for machine learning. Maybe we start to do that quality event forensic analysis across, and they're at that next level of maturity. And we've got customers who are moving pretty nicely on that. And then we've got a few customers. I think Ford Motor Company, for example, is doing a great job on this. They're the ones who have developed out those models and then actually deployed them into the stream, like I said earlier, right? So they're taking actions in real time. So real-time predictive models. You know, because, for example, you could do predictive maintenance and say, all right, I could run my models and spit out a report and say, you know what, these machines are going to fail within 3 weeks from a report. The next step would be say, no, let's put that model and put it into the vehicle, into the stream, and as soon as those conditions are hit, take a real-time action, right? Give a warning, tell the person they have to go to the dealership. You get the idea. So the companies who are actually doing real-time streaming analytics are at the highest level of maturity, and there aren't a lot of those, okay? Again, so what I said, most of the industry is still in that awareness exploration phase. We've got some great leading customers who have set some good guideposts for where the industry is going, but you know, start small, grow out the capabilities is the bottom line here. All right, so last slide, you know, why open source? You know, we think open source is really important just from sheer economics, right? The volume of data is going, as you can see, is going up to 16 zettabytes in 2017, so we've already passed that. But I propose to you, just if you are paying the old way per record for business, to store, the economics don't make sense. Open source doesn't work that way, right? It's open source, right? So the economics is one consideration. Just the rate of innovation in the open source community. No single vendor could keep up with the rate of innovation that's happening in the open source community. It always continues to amaze me just how much the rate of change we're seeing. And the other thing is for companies who are investing in IT solutions, it's lower risk because you're not going with any single vendor. You're not going to have a vendor lock-in. So hopefully this presentation has just kind of explained why Industry 4.0 is suddenly important, why data is important in that journey, right? And you know, the fact that many customers are doing that, and open source technologies are being used widely across those industry use cases. So I could see that I'm getting pulled from these guys that were running low on time. Questions or comments? Does it make sense? All right, guys. Thank you.